Okay, I want to recap some stuff we did at the very end of last time. Last time we talked about two little subroutines that you could do. I mean, they're 2 lines long, but we're really going to start thinking of them as like basic units. Both concerned with measuring a qubit. So one of them was this notion of extracting in a non-standard basis. So usually when you extract, you get either 0 or 1, and that's associated with the horizontal and the vertical, basis vectors. But we saw with like a tiny subroutine, you could simulate this other idea called extracting in a non-standard basis. And this you can do when you have a fixed basis in mind. In this picture, the basis is ket G and ket H, these 2 perpendicular vectors, blue and red. And then you can do this little subroutine called extracting in the GH basis. And what happens when you put in a qubit whose state is ket V? Well, you just kind of tilt your head such that it looks back like the usual 0, 1 picture, and then you do what you always did. So you compute the coordinate of the state vector V on the G vector, which is G inner product or G dot product V. And the square of that is the probability that when you do this measurement, the output will be G. And you also compute the other coordinate, the coordinate of V on ket H, that's H dot product V. And the probability that you'll see the outcome H when you do this measurement is the dot product of H and V squared. So it's like, again, the coordinate squared. And if you like angles, then this length here is cosine of the angle between V and G. So the probability of seeing G when you do this measurement is also cosine theta squared. And the same thing holds for outputting H. So the angle between V and H is 90 degrees minus theta. So the probability that you see H when you measure is cosine of 90 degrees minus theta squared, which you might also note as sine theta squared. Or alternatively, we know it's this height squared, this coordinate squared, and by trigonometry, this is sine theta. Okay, so that's a little routine that you can do. It doesn't seem like much, but we'll be doing it a lot. And of course, you can implement it in real life just by taking V and rotating it, whatever this like 10 degrees is in this picture, so you get back to the normal picture, extracting the normal way, and changing the output from 0 to G and 1 to H. So that's one little subroutine. Another one is what's called non-destructive measurement. So in our pseudocode, when you do extract on a qubit or any qubits, they get deleted. But for some, but not all, physical implementations of measuring or extracting a qubit, the qubit might still be around physically. And in the case that your physical qubit is still around in your apparatus, then that's termed a non-destructive measurement operation. But the state of the qubit changes after you measure it. And the state of the qubit changes, or some people say collapses to, just whatever state the measurement outcome was. So if you looked at the readout on your measuring device and it said 1, then the new state of the qubit, which now still exists, is ket 1, like all amplitude on ket 1. And in some sense, it's not really a new thing, because we can also simulate this using the pseudocode we have. We just do the normal extract, which deletes the qubit. Everywhere here, I'm imagining only 1 qubit, which deletes the qubit. And then you see either 0 or 1. And then you can remake this qubit yourself in that state. So you can simulate a non-destructive measurement yourself. But going forward, we may allow ourselves, because sometimes we can do it physically, and like in any case, we can do it programmatically. Sometimes we may allow ourselves to just do this non-destructive measurement operation with the qubit not getting deleted, but having a changed state. Okay, so in this lecture, we're going to be talking about some fun and games regarding kind of like a teeny tiny computational learning problem, which is trying to learn the state of a single qubit. And so in this algorithms for this, we're going to really be involving a lot this idea of trying to measure the qubit in different bases. So we want to get some practice with that. So I'm going to tell you about these. I showed them for like 1 second at the end. I'll show you about these like pieces of black plastic that you can buy for like $1 at your favorite online retailer. This thing is called a polarizing filter. It's also the thing that's like inside your sunglasses or your 3D movie glasses. Okay, so a polarizing filter. It's cool because it's like an actual physical measuring device for qubits that you can hold in your hand. So it has like, if you look at it carefully, it has some like chemical polymers or something in it. I don't know how it works, but like they're somehow in like long chains like this. And like if I hadn't like cut it out, I could have known which way is which. But if you hold it like this, where they're going horizontally, this thing performs, it's kind of weird. We talked about non-destructive and destructive measurements. It performs a semi-destructive measurement on qubits that are encoded by the polarization state of photons. So when it's held horizontally like this, I'm going to call this like a horizontally polarizing filter, HPF. It performs it in the standard basis. How do I want to write this? The standard basis just means 0 and 1, where so we're going to sort of think about it as like extracting in a potentially non-standard basis, but here the basis is just the normal one. So this G is 0 and the H is 1. And so this G being 0, which is like horizontal, that corresponds to this being horizontal. And why do I call it semi-destructive? Because the way it somehow physically works is it's like it measures the photon, and if the measurement outcome is G, which is 0, then it goes through. The photon like passes through, which is nice because then you can see it. On the other hand, if it does the measurement and the measurement outcome is 1, then like the photon like kind of heats up the square, but it like doesn't go through. It's blocked, so you don't see it. Okay, and in some sense, it's kind of funny because like if the measurement outcome is 0, it's like it's not deleted, and if the measurement outcome is 1, it's like it is deleted. So that's why I say semi-destructive. So that's cool. But what's additionally cool, by the way, you can like look through these. What's additionally cool is if you like get it, so you're like, oh, here it is, my horizontally polarized filter. You can like physically like rotate it with your hand, and like as you physically rotate, it changes into like a polarizing filter, but where G and H are like rotated, just like this. So I mean, like, if you want to implement the algorithm of measuring a different basis, you just like turn it. Okay, so I'll write that just to be clear. So if you rotate it physically by angle alpha, you get a semi-destructive measurer. So semi-destructive measuring device for another basis where, the G vector is, rotation by angle alpha of horizontal, and the H1 is rotation by angle alpha plus 90 degrees of 0. Okay, so just so we're clear, I have this circle picture here, and these percentages show the probability a photon or a qubit whose state is at this angle would like pass through a horizontal filter. Which is really nothing more than this. It's like literally cosine of the angle being depicted squared. So if you pass in a photon whose state is ket 0, which is this horizontally wiggling one, then there's like a 100% chance it will pass through. And if you have this horizontally polarizing filter and you pass into the state qubit whose state is ket 1, which is like vertical, then it's a 0% chance it'll pass through. If you pass in a photon whose state is ket plus, this direction, by the way, is ket plus, so at 45 degrees, then the probability it'll pass through is 50%. It's cosine of 45 degrees squared. It's kind of clear by symmetry. So it'd be a 50% chance of it passing through, and a 50% chance of it getting blocked. And yeah, by the way, that's the exact orientation of photons that come out of my cell phone and somebody else's cell phone we tried it on, and maybe your cell phone too. One thing I really want you to notice here is that this is not linear. If you go along this boundary. So it is true that if you go like halfway from here to here, it's like half the probability. But if you go a quarter of the way from here to here, I mean, pardon my diagram, but like it's not 75% here. Here it's like 85%. And if you go like 1/100th of the way around the circle, which is from here to here, that's 3.6 degrees, you know, it's not like you lost 100th, you lost 1,000th, okay? And this is all because of this square. So the angle is tiny. Like here, if the angle is tiny, then the probability is like the square of the angle, basically, which is much tinier. I should add, of course, that like, for example, over here, if the state is like this, it's also 100%. Okay, that's like saying if you measure, you know, this state, -1, 0, in the standard basis, what's the probability you get 0? Well, it's like -1 squared. Okay, or similarly, you know, this will be, this will also be 50%. That's like this negative, ket negative. That's -√1/2, +√1/2. If you measure this in the standard basis, the probability of getting 0 is the square of this number, which is indeed 1/2. Okay. So I want to try a couple of experiments with these little polarizing filters, because it's fun, and will also teach us stuff, actually, about quantum algorithms. So let me start writing it over here. Actually, I'm going to do a few experiments. The most complicated experiment is like the first one, which is just letting light from the overhead ceiling pass through the filter. Okay, so let's say experiment 1. Pass what I'll call like random light through this horizontally polarizing filter. And what I mean by random light, just like this light, which doesn't have any special polarization, which means that like a good way to model it is like, okay, there's zillions of like photons streaming out of these things, and they have no special polarization. So you just imagine their polarization, their state angle is a random, it's random on the circle. Okay, this is the one, again, that has the goes through measurement outcome being ket 0. So you can think of it like this. We're kind of analyzing this code, like new qubit A. Actually, the lights are doing this new qubit A like zillions of times. And then let theta be just a uniformly random real number between 0 and 1 times tau, which remember is 2 pi. So theta is like just a uniformly random amount around the circle. And then we'll imagine we do like rotate theta on A. Okay, so this little subroutine just gives us like a new qubit whose state is like a random angle. And then let's say we do this. Let's say now we pass it through. This is not really our pseudocode, but we'll apply the horizontally polarizing filter. So when we do this, like some of the photons get blocked and some of them pass through. Can somebody guess the fraction of photons that pass through? Yes? Yes, that's right. That's a good guess. Maybe extremely strictly speaking, you need calculus to prove that, but I think it's pretty intuitive, and I'll give you an explanation that I think will satisfy you. So the claim is that here, like the probability that qubit, a photon like this, passes through, which is like equivalent to like the measurement outcome being 0, is 50%. And why is that? It's because like this picture is symmetric along like this diagonal line. Okay, so it's true, like by chance, like the photon might come out pointing really close to horizontal, and then that photon would have a 100% chance of getting through. But somehow, like, it's equally likely that it would come out pointing like really close to vertical, and in that case, it would have like a 0% chance of going through. Okay, and similarly, like the photon might come out around here, in which case it would have a 75% chance, but it's equally likely to come out here, in which case it has like a 25% chance. And like, 75% and 25% average to 50%, and same with this and this. Okay, so, well, it's also kind of intuitive, but it's just saying like if you pick a random point on this circle and look at like the label here, like, I don't know, this one would be, again, 6.7%. We have like 25%. If you pick a random point around this circle and average the percentages, it's 50%. Okay, I think that's hopefully pretty believable by symmetry. Okay, so that's that, and therefore the probability that it's like blocked, which is equivalent to getting measurement outcome 1, is also 50%. Okay, which means, in principle, like if I hold this filter up and like look at the lights, like it should be literally exactly half as bright, like when I look through the square as when I like don't look through the square. Maybe like sometimes people like to do it with a laser pointer because like there you're really shooting photons like straight at it, and you could try to measure the intensity. But I don't think it's necessary. I think you could just look at like the lights through your eye. And it should also be the case, probably by symmetry, right? If I rotate it, it shouldn't really matter. That's kind of like if I like turn this circle around, it shouldn't really matter to the fact that the average is 50%. Okay. Any questions about that? Now, when I like look like this, and I'm looking through this, and I'm getting 50% of the light, all the photons that are hitting my eyeball are in a certain quantum state. What is that quantum state? Do you want to say? You want to say again? Yeah?
Zero.
That's right. It's ket zero. It's horizontal, because this is how it comes through. The ones that pass through, it's like they, collapse or get remade to zero. Okay, so like all the photons coming through this are in the state 0. In fact, if you ever wondered in your life, like let's say I'm trying to make a quantum computer with like photons, which is a great idea if you only plan to have one qubit. If you plan to have more than one qubit, it's not so great because it's hard to entangle photons. But with one qubit, you might wonder like, oh, how do I implement new qubit? This is supposed to like, make a qubit that's definitely in the state 0. That's it. You just put like this in front of a light source, and then all the qubits that are coming out are in the state 0. That's nice. Okay. Yeah, let me draw that, and then we'll talk about experiment 2. Okay, so in fact, let me draw it up here. Like we have some light. This happy little character is the sun, and it puts out some photons in like random angles. And then if we put in this like horizontally polarizing filter, then all the qubits that make it through are horizontal, and maybe this is like 50% intensity. So in experiment 2, put now in front a vertically polarizing filter. And this kind of means one where like you've rotated it, or actually I'm going to reflect it, where like the G vector, the measurement outcome that corresponds to going through is ket 1, and the H vector, the perpendicular one that corresponds to getting blocked, is ket 0. Which, if I want to do it, like if this is horizontal, then I can do it by reflecting, I think. You can also do it by rotating 90 degrees. That'll make one of these actually negative 0. But if you think about it, you're going to get the same results with negative 0 as you do with 0. Okay. So say I do that. I put this like vertically polarizing filter here, which I can depict like this. And then I ask, what's going on here? Yeah, so what is going on here? What fraction of the photons make it to here? Yeah. Yeah, that's right. Then 0% of the photons come through. I mean, make it all the way through. And why is that? Well, every photon that comes through here is in the state ket 0. It's kind of like in our picture, V is ket 0. And then it gets measured in this 1, 0 basis. So like the probability it passes through is, well, it's the square of some dot product. And it's the dot product of the state with this measurement outcome that we care about, 1. This dot product is 0, right? It's the dot product of this vector and that vector. That's 0 squared, which is 0. And indeed, like I have 2 of these. We can try it. Well, I don't know if you can see it so easily. I don't actually know if, like, let me get the better one. I mean, this is either horizontal or vertical. I'm not sure because I can't, like, stare at it. So we can just try it. Like, oh, this must be, like, horizontal in front of vertical. So it becomes black. Here's, like, kind of 50% grayscale. Now it's black. Conversely, if I rotate it this way, in principle, like, it should look exactly the same. Because there's, like, some plastic and imperfections, it gets, I think, a tiny bit darker, but, like, it should be exactly the same. I'll pass these around. You can play with them once I'm done making my points. You should also try putting them in front of your cell phone. Okay. So here, in this case, like, 100% of the light is blocked. We get down to, like, 0% intensity. Okay. But now for the final fun and games, and everybody likes to do this experiment on YouTube, so you've probably even seen it before. And I kind of did it last time in a different form. But now let's take our let's rotate a third horizontally polarizing filter by 45 degrees. And stick it in the middle. Okay, so stick it right in here. I'm not tall enough for this. I think I should have drawn the diagonal stripes the other way. Well, anyway. Okay, so what does this mean? This measures in the basis plus and minus. Yeah, let me say by negative 45 degrees. Plus and minus. Like this is plus, this one is minus. And let's say this one is the G and this one is the H. Okay, so this is if you get measurement outcome plus, it goes through. If you get measurement outcome minus, it turns into heat and gets blocked. So we can now ask, okay, what fraction of light makes it all the way through? Okay, and if you're a very naive person or you don't know about quantum, you're well, I have these 2 pieces of plastic. It's blocking all the light. I see blackness. Now if I put even more plastic in the middle, surely the light will only be blocked even more, right? But that's not how it works. So we can calculate, after the first horizontal one, that should be a HPF. Every qubit is in the state 0, which is horizontal. But now we're having it go through the diagonal one. So what's the probability? It passes the diagonal filter, which is the same as the measurement outcome being plus. Okay, well, we see from here, it should be cosine of 45 degrees. Which, it's a half, right? It's actually sort of the exact inverse of this. Here we're taking something that's in this state and measuring it along this angle. But it's the same result as taking something in the diagonal angle and measuring it with the horizontal vector. So anyway, this is plus 0 squared, which is a half. So that means that everything coming out here, half of these photons come out here. So actually, moreover, anything that comes out is in the plus direction. So we have like 25% intensity here. Like half of them made through the first one, half of them make it through the diagonal one, and the ones that make it through the diagonal one are all, ket plus. And then we have a similar calculation, like any, qubit passing the diagonal thing is in the state ket plus. So then what's the probability it passes the vertical filter? Okay, there's the probability that you measure ket plus and you get 1. Again, this is 1 inner product plus squared, which is half again. Because again, vector ket 1 and vector plus are at 45 degrees. That's cosine of 45 degrees squared. Okay, it means like half of all these photons make it through here. If they do make it through here, they're all ket 1s. But we get half of 25%, so this is like 12.5%. Okay, so this is like the kind of cool paradox that is like a real quantum experiment you can do with your hands. We can try to see it. I'll show it to you. So we set it up. Here's horizontal and vertical, so they're blocking themselves. Like no light is getting through. And then if we insert this diagonally, this will be easy when you're holding it in your hands, but you can try to see it. Actually gets somewhat lighter. You can't see through it. You put the one in the middle, and now you can see through it. That's pretty cool. You can try it yourself.